Good morning all of you. Today we will start the design of doubly reinforced beam. After this session, you will be able to define a doubly reinforced section, explain the need of providing doubly reinforced section, draw the stress strain diagram of doubly reinforced section, calculate the moment of resistance of doubly reinforced section. So first let us discuss what is a doubly reinforced section. When steel reinforcement is provided both in tension as well as in compression zone, then that type of section is known as doubly reinforced section. Then what is the need of providing this doubly reinforced section? We need this section because we could not provide the required depth if we will design it as a singly reinforced section, as the depth is sometimes restricted due to architectural point of view, and also in order to increase the moment carrying capacity, that is known as moment of resistance MR of a section. Then what is the design philosophy of this doubly reinforced section? So this is a beam section which is reinforced in both tension and compression zone. This is width of the beam and this is effective depth of the beam. So this doubly reinforced beam subjected to a moment mu. This is subjected to moment mu, and this can be expressed as a rectangular section with tension reinforcement AST limb This doubly reinforced section can be expressed as a rectangular section with tension reinforcement AST limb for balanced condition, giving moment of resistance mu limb plus an auxiliary section with reinforcement in compression zone ASC, and also tensile reinforcement AST2, giving moment of resistance mu2, such that this mu will be equal to mu limit plus mu2. For the moment mu limb, this mu limb, the tension steel, for this moment mu limb, the tension steel AST limb is found out by as explained for singly reinforced section. For the additional moment mu2, the additional tension steel and additional compression steel are provided such that they give a couple of moment mu2. So let us draw the stress strain diagram of doubly reinforced beam. This is your compression reinforcement, and this compression reinforcement is provided at a distance of d dash from the extreme compression fiber, and this is your effective depth of the beam. This is denoted as compression reinforcement ASC, and this is your AST. This is your depth of neutral axis, denoted as XU. This is your neutral axis. This is the strain diagram with extreme strain at concrete fiber 0.0035, and the strain in steel is 0.87 Fy by ES plus 0.002, and this is the stress diagram. The stress in concrete at extreme compression fiber is 0.446 FCK. Here the steel is 0.87 Fy. This is T. Here, so this stress strain diagram, this is the section of the beam, this is the strain diagram, this is the stress diagram. So this stress strain diagram is nearly same as your singly reinforced section, but the difference is that there are two kinds of compressive forces acting in case of a doubly reinforced section. So as you know before, this C1, this is the compressive force taken up by your concrete. So C1 is the compressive force taken up by concrete. Okay, and this C1, as we know before, it acts at a distance of 0.42 XU from the extreme compression fiber. So its lever arm will be D minus 0.42 XU, and the second compressive force is carried out by the compression steel. So this compression steel is acting provided at a distance of d dash from the extreme compression fiber. So the corresponding force is acting at a distance of d dash from the extreme compression fiber, and the lever arm for this force will be d minus d dash. So C1 is the compressive force taken up by the concrete, and C2 is the compressive force taken up by the compression steel. So as you know before, this C1 is equal to 0.36 FCK BXU. That is the compressive force taken up by our concrete. And C2 will be calculated as multiplying the area of compressive reinforcement AC with the corresponding stress in compression reinforcement FSC. So this C2 will be taken as AC into FSC. So the total compressive force C will be equals to C1 plus C2. So in place of C1 we can write 0.36 FCK BXU, and in place of C2 we can write it as FSC into AC. So referring to the stress diagram, refer the stress diagram of doubly reinforced section. So in order to put this section in equilibrium, we must assume that the total compression, that is C1 plus C2, must be equal to the total tension. So this total compression will be equal to total tension. So this 0.36 FCK BXU plus AC FSC will be equals to 0.87. Total tension is, so total tension depends upon the reinforcement, the stress in steel into area of steel. So this area of steel AST will be equal to AST limb plus AST2. So total AST where this AST is equal to AST limb plus AST2. This is equation 1. Then calculation of moment of resistance. So this moment of resistance, as we know before, is the moment carrying capacity of a section. So the moment of resistance in doubly reinforced section can be found out by taking moment of compressive forces. What are the compressive forces? C1 and C2. By taking the moment of compressive forces C1 and C2 about the centroid of tensile reinforcement. Clear? So the first, and this mu is equal to mu limb plus mu2. So first, what is this mu limb? So this mu limb is the compressive force carried by the, and this is the moment carrying capacity of the concrete. So what is the force in concrete? 0.36 FCK B XU max into D minus 0.42 XU max. This is the force and this is the lever arm. So the lever arm multiplied with the force giving the moment of resistance. And then second one, mu2, is the moment carrying capacity due to the compression reinforcement. So the force is ASC/FSC and the corresponding lever arm is D minus D dash. So by multiplying this, we are getting the mu2. So total moment carrying capacity of the section will be 0.36 FCK B XU max whole into D minus 0.42 XU max plus ASC FSC D minus D dash. So in this way we can calculate the moment of resistance of a doubly reinforced section. Thank you all.